Welcome to this tutorial. We are trying to see why in the case of condensed phases you can assume that the internal energy and enthalpy are more or less the same. In other words, the effect of pressure and volume changes need not be calculated at all. So, this tutorial is based on introduction to thermodynamics of materials by Gaskell. So, the edition that I have, which is the 4th edition, page number 134 to 136, this is described, and that is what we are going to follow. So, the idea is as follows. So, let us say that I take a system from state P1T, so to state P2T. Now, I want to calculate what is the change in enthalpy associated with this change going from P1 to P2. Let me call that change as delta H, that is an integral from P1 to P2, that is V times 1 minus alpha T times dP, where V is the molar volume and alpha is the isobaric coefficient of thermal expansion. Okay. Now, if you take the example of iron, for example, suppose if I say I am considering iron, V is some 7.1 into 10 power 6 meter cube, this is the molar volume, and alpha is 0.3 into 10 power minus 4 per Kelvin. So, if you use these two values and if you see that suppose if P1 is 1 atmospheric pressure and P2 is 100 atmospheric pressure, you can calculate this quantity and you can show that delta H is of the order of 71 joules, but this is for changing from 1 to 100 atmosphere pressure. On the other hand, you can achieve the same 71 joule change in the enthalpy by changing the temperature. If temperature changes from 298 to 301 at P is equal to 1 atmosphere, you will get the same change in enthalpy. In a similar fashion, of course, you can also calculate the change in entropy, and that is given by again for a change of 1 atmosphere to 100 atmosphere. So, that is going to be of the order of minus 0.0022 joules per Kelvin, and this change in entropy, for example, can be achieved in iron from 298 Kelvin. Suppose if you reduce the temperature, decrease the temperature by 0.02 degree, okay, at 1 atmospheric pressure. In other words, the changes that are associated with pressure and volume and in the entropy and enthalpy are very, very small. In fact, smaller temperature changes will cause much greater change in entropy and enthalpy. Of course, because these two are integrals, the delta H also what I wrote was an integral. So, P1 to P2 V 1 minus alpha T dP. It is possible that the molar volume and the alpha, the isobaric coefficient of thermal expansion, are pressure dependent. So, they can be made functions of pressure, and similarly here alpha P Vp dP. So, it could be some polynomial that you are trying to integrate. Again, if you are going to be looking at very small changes in pressure, and typical changes that we have been talking about is between say 0 atmospheric pressure and 1 atmospheric pressure. So, in that range, this change in alpha or V with pressure is also very negligible, and unless you are going to have very large changes in pressure, of the order of 100 atmospheric pressure change, but even that is going to produce changes in enthalpy and entropy which are achieved by fraction of a degree to a few degrees. So, this is the reason why in condensed systems, that is liquids and solids, we always assume, we make this approximation, that is H is U and rather delta H is delta U. So, this is one of the approximations that we have made, and this is a valid approximation for this reason. We have taken the example of iron, you can take any other example, it does not even have to be a solid, you can even take the case of a liquid. Molar volume changes are not very much, and expansion coefficients are not large numbers. So, because of which we always find that this approximation is a very good approximation. Thank you.